The inverse trigonometric functions. So we've studied the trig functions, sine, cosine, tangent, cosecant, secant, and cotangent. What these trig functions do is they are a function, they are an operator, that takes an angle to a ratio of sides. And that ratio depends on whether it's sine, cosine, tangent, or the reciprocals. They have understood ratios of sides. For instance, sine goes to the opposite side over the hypotenuse. But what we know about math is that everything in math has to have something to undo it. There has to be a way of undoing it. And that is where the inverse comes in. That is what an inverse does. It undoes a function. So our inverse trig functions, they're going to take the ratios of sides and send them back to angles. So these will take a ratio of sides back to the angle. They're undoing that original trig function. Really make sure that you understand what trig functions do. They're not just these random things that turn one number into another number. They have a very specific purpose. You input an angle, you have a ratio of sides as an output. Inverse trig functions, you put in that ratio of sides, you get back an angle. Oftentimes I see just students' lack of understanding of those basic ideas will kind of set you off track for the entire class. If you don't understand that basic idea of what a trig function does and what an inverse trig function does, it makes everything else related to them very, very challenging. So make sure you get those basic ideas. Now, let's start with the inverse sine function. So I'm going to start by drawing a sine wave. Now, as we've discussed recently, it's challenging to draw a sine wave because it is infinite. It keeps going on forever and ever. And so for that reason, we have a problem. Because to have an inverse, a function must be, remember, 1 to 1. 1 to 1 meaning for every x there is a unique y. And if we look for sine, if we look at, for instance, 0, we see that we get 0 at 0 and at pi, and at 2 pi, and at 3 pi, and at 4 pi. That is not unique. In fact, every single value on this sine wave fails to be unique. So what we're going to have to do to start with is we're going to have to restrict this sine function. Going to restrict this sine function in such a way that we are getting a one-to-one function. So I definitely need to make sure I have all y values. So I definitely need to have the positive y values. And I'm going to backtrack a little bit on my graph. I'll get back to negative pi over 2. And at negative pi over 2, we have a negative 1. Pi over 2, we have the 1. So between negative pi over 2 and pi over 2, we get all y values. We get an entire range. The range for sine, remember, is negative 1 to 1. We have all of that inside this restricted domain. And so what I've done is I've taken the unrestricted sine function that goes from negative infinity to infinity. I've restricted its domain to being between pi over 2, negative pi over 2 to pi over 2. And that way, this little portion in here becomes 1 to 1. So what I want to look at next is I want to look at this inverse sine function's graph. And remember, what does an inverse function look like? It is simply the flipping of those x's and y's. It's taking the outputs and making them the inputs. Or we can think of it as a reflection over the line y is equal to x, same idea. But I'm going to think about it in terms of flipping points. So initially we had this point, negative pi over 2, negative 1. And it should be noted that pi over 2 actually is much larger than negative 1, not much, but it's about 1.5 times negative 1. So we always do these sine graphs kind of out of scale. Really, the negative pi over 2 would be a longer direction, meaning that when I flip those directions, negative pi over 2 should be bigger than the negative 1. So that initial point that we had of negative pi over 2, negative 1 is going to become negative 1, negative pi over 2. If we flip 0, 0, that stays 0, 0. And then finally, we're going to have 1 pi over 2. And connecting our dots to make sure that we have our curves the right way, this would be the graph of the inverse sine function. So the inverse sine function is taking y values are ratios of sides of -1 to 1, -1 to 1, and it's sending them back to the angles, the outputs now being the angles between -π/2 and π/2. So we can see the inverse sine function's domain goes from -1 to 1. Its range goes from -π/2 to π/2, simply switching what we had from before. We'll do some examples with these more in a second. I will point out before I move on though, I can apply any of the transformations that we've applied up to this point. So if I had, I'll do it in blue. If I had y is equal to inverse sine of x minus 1. Well, I know that the x minus 1 there is causing a shift to the right by 1. So I'd take all my values from before, I'd shift them to the right by 1. Now we have this point at -π/2, and we'd have a point at 1, 0, and then finally the last point would be 2π/2, and we'd have our curve. If we had a plus pi on the outside, tacking on another term out here, plus pi, well, that would be taking this and shifting everything up by pi units, right? So all those transformations work the same as we've seen before. That shouldn't be very hard. Let's move on to Cosines Graph. If I think about what cosine looks like, I didn't actually label this one as sine, so let me do that. Y equals sine x. So here we have y equals cosine, and we know that this again is an infinite graph starting at 0, 1, and by the time we reach 2 pi, it gets back to that high mark of 1. At pi, it has its low mark of -1, hits its in-betweens at π/2 and 3π/2, 3π/2, and so we'd see a curve that looks like this. And of course, just like with sine, it is infinite, it goes on forever and ever. And so we run into the same problem that we did with sine, where this is not a one-to-one function, so it does not have an inverse. So if we want to get an inverse, which we need to be able to do, we need to restrict it. This is not a new idea. This is the same thing we did with x squared. Remember, x squared, y equals x squared, not one-to-one. So we said, all right, let's just take that right-hand half. So for cosine, again, I need to make sure I have highs from -1 down to lows of, sorry, I said highs of -1, but highs of 1 down to lows of -1. Notice that happens between 0 and pi. So to restrict my cosine function, I'm going to do so between 0 and pi. That will give me the entire range of the cosine graph, which goes from -1 to 1. I have to be able to undo any ratio of sides. Ratios of sides span from -1 to 1. I have to be able to undo any of them. Well, going from 0 to pi will do that. If I were to graph the inverse cosine function, well, we're going to do the same thing we did before. We're going to take those values. So we had the value of 0, 1. That becomes 1, 0. The next value we had was π/2, 0. That's going to become 0, π/2. And then the final value we had was the down here at pi -1. So that's going to become -1 pi, running off my axis a little bit. I'll squeeze it in up there. And then drawing my curves, this would be the graph of the inverse cosine function. Again, apologies for the lack of perfection, but you get the idea of how these are connecting. So these would be -1 and 1. We had 0 to pi up here by my function. And from there, we can apply the same transformations the same way. If we look at our range, let's start with the domain. The domain goes from -1 to 1, and then the range of this inverse function goes from 0 to pi, just switching what we did from before. And then finally, I'm going to look at tangent for now, because we know if we have reciprocal, we can just turn those into the reciprocal. So for instance, secant is somehow related to cosine. We can just turn that into the cosine. We'll look at those a little bit later on, but I'm not going to draw their graphs. So tangent goes through 0, 0. It has asymptotes at -π/2 and pi/2. And of course, there are infinitely many waves. I'm just going to do a quick sketch of a couple of them. But here's the thing with tangent. It very nicely sets itself up to be restricted. Very clearly, we can have a full wave between the asymptotes of -π/2 and pi/2. So I'm going to restrict this tangent I'm going to say its domain has to be between negative pi over 2 and pi over 2. And that gives me the entire range, the range of tangent being negative infinity to infinity. So when we think about the sine, cosine, and tangent graphs, absolutely, their domains are not restricted. Sine, cosine, negative infinity to infinity, tangent, negative infinity to infinity, minus the pi over 2's or any multiple thereof, any pi multiple thereof. But when we go to do the inverses, we've got to start by thinking about the restricted functions. All right, to look at the inverse tangents graph, those asymptotes of pi over 2 and negative pi over 2 become horizontal asymptotes because we're still switching the x's and the y's. 0, 0 flips over. We could think about another point in here. We'd have the point negative pi over 4, negative 1. So if we had negative 1, we'd have negative pi over 4. That'd be up here. Just getting a ballpark of what this would look like. There would be the graph of the inverse tangent function. We could shift that however we want to. But these domain ranges are going to be very important as we move forward. Notice we've chopped sine and tangent off in a very similar fashion. Sine and tangent, we said that the domains between negative pi over 2 and pi over 2, the only difference being tangent we can't equal those pi over 2's because that's an undefined value. The cosine, that one we chopped its domain off between 0 and pi. A little bit different, and that is important. So let's see how these can help us. Let's say I ask the question, find the inverse sine of, say, root 2 over 2. So based on my knowledge of trig functions, I know a trig function takes an angle to a ratio of sides. So what an inverse must be doing is taking a ratio of sides back to an angle. So I'm thinking to myself, when do I have an angle of root 2 over 2? So right away my mind should jump to the special triangles or the unit circle. I know that special triangles where I see a root 2 is at pi over 4. Pi over 4, if I took the opposite over the hypotenuse, have 1 over root 2, which rationalizes to root 2 over 2. So when do I see a ratio of pi over 2, root 2 over 2? That is at pi over 4. That is my answer. Now you might say to yourself, this is similar to what we've done before. We've already done something kind of like this, and we have. Before we were asking the question, when is sine theta equal to root 2 over 2? And we may have had restrictions on theta. So for instance, it may have said that theta was between, let's say, pi over 2 and 0. In which case, our answer would have just been the same exact thing. Because what is an inverse trig function asking us to do? It's asking us to find the angle that gives us this resultant ratio of sides. So it's kind of the same problem. Now I say kind of because what if I didn't have this restriction here? What if I hadn't told you where theta was? Well, then sine is equal to root 2 over 2 at pi over 4. That's still true. But then we'd also have to say, well, I know sine is positive in the third quadrant. So using pi over 4 as a ratio, as a reference angle in the third quadrant, I'd get 3 pi over 4. The ratio root 2 over 2 also occurs at pi over 4. But then, of course, I could use any coterminal angle as well. And so what I actually see is I get an infinite solution set. There are infinitely many things that will give us that ratio of root 2 over 2 for sine. With the inverse sine, because we have restricted the domains and the ranges for these things right away, we've really restricted the domain of the original sine function, we can only have that one answer. That is the one and only answer. That's the whole point behind an inverse function. Remember, to be a function, we have to have that clear path. We're going from x to y. We have to know what y we're going to get back at. An inverse, we have to be able to undo that. We have to know, well, if I'm starting at this y, I know exactly the x that I'm going to get. If I don't have that clear path, like I did down here at the bottom, it can still be a useful problem. It's still something that we will want to know, but it's just not the definition of a function. It's not how functions work. And so in inverse, we have to be able to undo that problem and get to just one answer. So anytime we're finding an inverse trig function, we will only ever have one answer. If I just left an open-ended question, when is sine equal to a given ratio, it could be infinitely many answers. Let's take another example. Let's find the inverse tangent of root 3. So again, I'm going to think about my triangle that would give me the ratio of sides involving root 3, and that occurs at the 30, 60, 90, or the pi over 6, pi over 3, pi over 2 triangle, special right triangle. You could also use your unit circle. So I want an opposite of root 3 and an adjacent of 1. And that would occur from the perspective of the angle pi over 3. So my answer is just pi over 3, the one and only answer. It's not like I had before where it's pi over 3 or any co-terminal angle or the angle that's in the third quadrant. No, inverse tangent is just the one single answer. Let's take the inverse cosine of negative 1/2. So this time we have a negative. Let's first think about the 1/2. So I'm going to ignore that negative for just a second. What we just saw, when do we see, sorry, I set that up wrong. When do I see the ratio of sides of 1 over 2? Well, that would be at pi over 3. The adjacent is 1, and the hypotenuse is 2. So it's going to be pi over 3 or close to. Now, the reason I say close to is because it's supposed to be a negative. Of course, pi over 3 would give me a positive for cosine. So how did we fix this before? Well, we said, well, where is cosine negative? It's negative in the second and in the third quadrant. So we would have picked that pi over 3 up, and we would have said, well, in the second quadrant, it's 2 pi over 3. Or in the third quadrant, it's 4 pi over 3. And then it could have been any coterminal angle thereof. But now we know that there can only be one answer. Why is that? Because it is an inverse trig function. So we have to figure out which answer is correct. Well, because cosine, remember, its domain was restricted to being between 0 and pi, that means it can only ever occur in the first or the second quadrant. Not thinking about the picture when it's stretched out, when we're going, from negative infinity to infinity on the domain, but thinking about the unit circle, where do we see that the cosine is negative 1, 2, 3, and 4? Well, it is negative in the second and the third quadrant, but what we just said is it can only exist in these upper two quadrants. That's the only place that inverse cosine is allowed to exist. So that means we have to be using the second. We need to be using 2 pi over 3, and that is our answer. Let's find the inverse sine of negative root 3 over 2. Well, negative root 3 over 2, we got to figure out where that occurs first. And so that occurs at the same pi over 3. So it's going to somehow be related to pi over 3. And so we need to be thinking to ourselves, well, we know in the first quadrant it's just pi over 3. In the second quadrant, sine is positive, so that doesn't matter. In the third quadrant, we would have 4 pi over 3, as we just defined. In the fourth quadrant, we'd have 5 pi over 3, and then any coterminal angle thereof. But we need to think about the restricted sine's domain. And remember how we restricted that way up here, as we had said that sine had to be between negative pi over 2 and pi over 2. Thinking about quadrants, where does that put the sine? Well, negative pi over 2 would be in the fourth quadrant, right? To pi over 2, past the first quadrant, puts us in either the first or the fourth. And so we're thinking 5 pi over 3. But that wouldn't be right because we've got to adhere to that exact domain. It had to be negative pi over 2 to pi over 2. 5 pi over 3 is not between those two things. So we need to use the coterminal version of this that puts us into the fourth quadrant. So negative pi over 3. We've got to make sure that we're always fulfilling the domain restrictions of the restricted sine, cosine, or tangent function. We can't just choose any angle anymore. We can't choose all the angles. We've got to have the one correct answer. And so for sine, we're thinking about being in either the first or the fourth quadrant. And to get to that fourth quadrant, we've got to use a negative angle. For the cosine function, we're thinking about being in either the first or the second quadrant. It's a little more straightforward. And then tangent, very similar to the sine, we're going to be in the first or the fourth quadrant using a negative angle to get there. So let's do one quickly with inverse tangent. Let's take the inverse tangent, let's say, of negative 1. And so where do we see a ratio of sides of 1 over 1? That would be at pi over 4. So we're thinking, well, pi over 4 is involved, but if we think about the quadrants, because it's a negative, what we just said is we have to use the first or the fourth quadrant version of tangent. It's going to have to be in the fourth, and we can only get there using the negative, so it's going to have to be a negative pi over 4. That would be our answer. We need to really make sure that we're comfortable with these domains and ranges. Let's talk about a couple of other things that we might see. Let's say that we have the inverse sine of 2. Well, what we've already seen is that there are a lot of values that we know the exact values for. So pi over 4, pi over 3, pi over 6, pi over 2, pi's, and then we're going to add even more to our list that we can find the exact value for. There are some that we just can't find the exact value for. So if I think about when do I see a ratio of 2 in the unit circle or in the special triangles, I don't see it. There is never a place where I see the y value of 2 in the unit circle or a ratio of 2 over 1 opposite to hypotenuse in the right triangle. Now for some values that might just mean that it's not an exact value. So for instance, if we were to take the inverse sine of 1/3, this is absolutely a doable value. This is something that exists. It's just not something that we can do as an exact value. We don't have that exact value. Inverse sine of 2, that just doesn't exist because remember what we said on the unit circle, the furthest we're ever going away from our center is 1 unit. This is asking us to be 2 units away. That's impossible. Or if we think about what this is saying on a triangle, is the opposite side is 2 and the hypotenuse is 1. The hypotenuse has got to be the largest side. This is always going to be impossible. So another useful way that we can use our domains and our ranges is to think about when is something possible. We can never take the inverse sine or cosine of something greater than 1 or less than -1. That will always be an empty solution set. Now coming back over here to the other one that I write up, the inverse sine of 1/3, this is absolutely doable, but this is something that we have to do in the calculator. And so when we type this into the calculator, we get a ratio of, we get an angle from the ratio. We get an angle of approximately 0.3398 radians. So it would be an approximation. I could also write it as 19.47 degrees, but again, it's an approximation. These are both approximations. So anytime we can find those exact values, we want to do so. If we can't, we want to think about, well, is it because it's impossible or just because we don't have an exact value for it? But there will be times that it's impossible. All right, let us move on to talk about the composition of trig functions. We've seen compositions of functions before, right? Let's say we had f of x is equal to 2x and g of x is equal to the square root of x. We can take the composition f of g. That would be saying take the g and plug it into the f of x, or just 2 square roots of x. Can do the same thing with trig functions. And I'm going to start with the easy ones. If we had 2 functions that were inverses of one another, f and f inverse, if we took their composition, that always left us with x. By the properties of inverses, f of f inverse is equal to x, which is the same as f inverse of f. Which means that if we were to take sine of the inverse, or the inverse of the sine of x, that should leave us with x. And that is mostly true. Let's think about why I say mostly. These statements would have to be true as long as we are inside the domain of the inner function. We always have to think about the domain of that inner function. We saw that again back in 171. If we were to take a function of, well, let me define these real quick. Let's say that f of x is equal to 3x, g of x is equal to 1 over x, and I were to say take f of g of 0, well, right away I can stop and say that's impossible because I couldn't plug a 0 into the denominator of this g of x here. And so we always want to make sure that we are adhering to the domain of the inner function. So remember, the domain of the sine function is negative infinity to infinity, but we said at the beginning when we started this discussion, we have to restrict that for the inverse. We restricted that for x in the interval negative pi over 2 to pi over 2. And then if we think about the inverse's domain, right, that was simply the range of the sine function. That was true for x in the interval -1 to 1. This is what we were just talking about a second ago. I can't find the inverse of something like 2 here because I'm never going to get that ratio of sides out of a triangle or out of the unit circle. If we were to take the inverse cosine of the cosine of x, that better equal x, but again with the restrictions on our domain for x in the interval 0 to pi. And then if we were to take the cosine of the inverse cosine of x, that better equal x as long as we're in that -1 to 1 interval. And then finally, if we were to take the inverse tangent of x, that better give us x. That better give us x for x in, well, remember what was the restricted tangents functions domain? -pi/2 to pi/2 without the points included. If we're to take the tangent of the inverse tangent of x, that's going to be equal to x. Now here's a nice one. For all x, because remember, tangent's range goes from -infinity to infinity, so the inverse, all things are possible, right? So this gives us a little bit of a shortcut when we start to do compositions. Let's say, for instance, that I were to have the problem sine of the inverse sine of 1/3. Well, I know the answer is 1/3. There's no work to be done. I know that that 1/3 is in the domain of my inverse trig function. The sign is in between -1 and 1. Let me do one that we can do the long way. 1/3 is actually not one that we can find an exact value for. 1/2 is. Let's think about this problem for a second. So let's pretend I had just this portion underlined in red. The inverse sine of 1/2. Well, I'm looking for what ratio of sides, what angle gives me a ratio of sides of 1/2. And that occurs at pi/6. So I could write this problem as sine of pi/6. And then of course sine of pi/6, what we just said, it's equal to a 1/2. The same logic applies to this first one, right? We'd find the angle that gives us a ratio of 1/3. Wouldn't be exact, but we'd have that ratio. We'd immediately take the sine of the ratio of the angle that gave us 1/3. So we'd get back to the same exact 1/3. Has to give us the same thing. Now, where will that change? Let's say we take the sine of the inverse sine of 2. Now you might say, well, they're inverses, it's going to give me 2. Well, absolutely not. There's no solutions to this for the reasons we talked about above. There's never an angle that's going to give me a ratio of sides of 2. So right away, this breaks down. We can't do this problem. Even though we have these shortcuts on our compositions, if we're taking a trig function of its inverse or an inverse of its trig function, what we're really doing is we're doing each thing separately. We are first taking the inverse sine of 1/3, and then we're finding its sine. We've realized a little bit of a shortcut there, but that's really the math that's going into it. Here we're taking the inverse sine of 2, and then we're taking the sine of that. But we can't do the inverse sine of 2. If I were to switch the order around a little bit, let's take the inverse sine of the sine of pi/3. Well, the answer is going to be pi/3. Why is that? Well, I draw out pi/3's triangle. That would be the larger angle up here. The ratios of sides would be √3/2. And so we'd have the inverse sine of √3/2. Well, where does that occur? Obviously at pi/3. That's what we just found it to be. Where will this be different? Let's take the inverse sine of the sine of 4pi/3. This is not going to just be 4pi/3 because 4pi/3 is not in the restricted domain of sine. It's not in the range of the inverse sine. So here, let's do this one the long way because that's the only way we can do it. 4pi/3, I need to start by thinking about my reference angle. It is pi/3. We could also use a unit circle. We get the ratio of sides of √3/2, but we would get a negative √3/2 because this is in the third quadrant. 4pi/3 is in the third quadrant. And so then we'd say to ourselves, well, when do we get an inverse sine of negative √3/2? Well, we do know it's going to be an angle of pi/3, but because we know that inverse sines domain, or the range rather, is from negative pi/2 to pi/2, we have to use the negative pi/3. This goes back to what we were doing at the very beginning finding those inverse trig functions domains and using that to find the values. So we can't just always assume that by taking the trig function of its inverse or the inverse of the trig function, we're going to get back to that interior x. It could be different based on the domain and the range of the trig functions. Now, we've talked a lot about the sine, cosine, tangent, but I haven't really done a whole lot with cosecant, secant, and cotangent. So what if I had cosecant of, let's say, 2? Well, I told you before we can think about these, and I want to do the inverse cosecant of 2. I told you we can think about these in terms of their reciprocal functions. And so I know that reciprocal for cosecant is sine. And so the question is, before I write this down, I guess our previous understanding was we just write it 1 over the sine, right? And that's completely false. Let's think about why that is. Cosecant x is equal to 1 over sine x. Think about what we have. We have a trig function, meaning x is the angle, and we are going to a ratio of sides. So this is a ratio of sides. This is a ratio of sides that's now under 1. If we're doing the inverse cosecant of 2, what this is right here is actually an angle. What this would be 1 over that angle. Reciprocal trig functions aren't the reciprocal of the angles, they're the reciprocal of the ratio of sides. So where is the ratio of sides in this problem? It's the 2. So if I want to write this as a sine, I can absolutely do that, but it's not as 1 over, it's as the inverse sine of 1 over 2. I have to do the reciprocal of the ratio of sides. And so then the inverse sine of 1/2 would be pi over, try that again, pi over 6, and that would be my answer, right? But the key to remember is if we're doing the inverse trig function of one of the reciprocal functions, we're not saying that cosecant is equal to 1 over sine inverse. We're saying that the inverse cosecant is equal to the inverse sine of the reciprocal of the ratio of sides. To take another one, let's say we had the inverse cotangent of negative root 3. Well, we could write this as the inverse tangent of negative 1 over root 3. The ratio of sides being the root 3, I've taken the reciprocal of that. And so then if I think about my special triangles, I know I've done this 1,000 times, but notice I'm still drawing out the triangle just to make sure that I get it right. So I want the 1 over root 3, that would mean I'm at the pi over 6 angle. Because it's a negative and its tangent, we would need to be in the 4th quadrant using that negative angle. So we'd have a negative pi over 6. Now that we've talked about these inverse trig functions, both of the initial 3 functions and their reciprocals, let's do compositions where it's not just a composition of its own inverse. What if I have the sine of the inverse cosine of root 2 over 2? Well, we can do this problem. We can do the inverse cosine of root 2 over 2. That would be pi over 4. I'm thinking about when do I get a ratio of sides of root 2 over 2. That is at pi over 4, or I can pull that out of the unit circle as well. And then I can do sine of pi over 4. It is root 2 over 2. Now, it's not to say that taking the sine of the inverse cosine is equal to the initial value. That's only ever true actually for this one example. If I were to do sine of the inverse cosine of 1/2, well, when do I get cosine to be a ratio of sides of 1/2? That's at pi over 6. So we'd have sine of pi over 6, which is equal to root 3 over 2. So there's my answer. So notice, if we have these mismatched trig functions, we just have to do the math. We do it the long way. We could have done that same math the long way for all of these ones who are taking the trig function of itself. It's just we didn't have to. We know that if we're taking a trig function of its own inverse and it meets the domain requirements, we get to use that shortcut of just getting the interior. But we can always just work it out. That's always going to give us the answer, and that's what we have to do for these mismatched trig functions. What if we have something where we don't know what the angle is? So let's say we have the cosine of the inverse tangent of 2/5. Well, I have no idea where a ratio of 2 over 5 occurs. I could find it if I wanted to. I could type this in the calculator and get an approximate value, but I don't want to. I want to use exact values, so I'm going to think about this in terms of its picture. Tangent is equal to the opposite over the adjacent. This is whatever the angle is that's at the heart of this problem. I can find the third side by just using the Pythagorean theorem, so I'd have 25 plus 4 is 29, and take the square root of it, 29. And so I know that this inverse tangent is going to give me theta. I don't know what theta is, I don't really care, because I immediately want to know what cosine of theta is, and cosine is equal to the adjacent over the hypotenuse. So I could rationalize that if I want to, but I'm not going to. If I were to take the sine of the inverse cosine of 1/9, we'd start by drawing the picture. 1, the hypotenuse is 9, and I got that on the wrong side. If my theta is here, my adjacent should be 1. Well, that would mean my opposite is the square root of 81 minus 1, which is the square root of 80, which I can simplify to 4 goes into that. Actually, 16 go into that, I think, 5 times. So 4 square roots of 5. And so we could write this answer as 4 square roots of 5 over 9. So once we understand what we have in terms of an angle or a ratio of sides, it is just drawing that picture, thinking about what we're looking for. That's what we're doing. Cosine gives me 1 over 9. Well, I can find the third side using the Pythagorean theorem, and then I know that the sine is equal to the opposite over the hypotenuse. One final idea that I will leave you with, and we've already seen this a little bit, and we're going to see this a little bit more. Let's say I want to find theta to get to an, rewrite this a little bit. Find theta given that the terminal side passes through -2, 4. So the first thing that I would do is draw this picture, right? -2, 1, 2, 3, 4. It's going to be up here. So I want to find a theta to take me here. And so we've done problems like this before. We know that the x is -2, the y is 4. So if I want to think about the trig function that solves this problem, tangent theta is equal to the opposite is 4 over -2, or the y over the x. And so I type this in my calculator. We'd have the inverse tangent of -2, which is possible, because remember, its tangent's domain is from -infinity to infinity. So this is possible, it's just not an exact value. And so we get the angle from our calculator of -63.43 degrees, or we could use radians, -1.107. I'm going to stick with degrees for right now. If I were to think about this angle, -63 degrees is down here. Not at all what I want. The calculator doesn't know whether an angle is supposed to be in the first, second, third, fourth quadrant. Notice we were never asking for the inverse tangent, but that's what we used. Right here when we went to solve this, we set up a problem, the inverse tangent of 4 over -2, or the inverse tangent of -2. And what we now know is that every single time we do this problem, the calculator knows the rules. Every single time we do this problem, the calculator is going to put into the fourth quadrant because it's a negative. But that's clearly not where this angle is supposed to be, so we have to be the ones to make that correction. We have to be the ones to say, all right, let me treat that 63 as a reference angle. I need to move that into the second quadrant. I can do that by subtracting it from the 180, and I get 116.57 degrees. And that is an approximate. Let's try that one more time. 116.57 degrees. And that looks better because that is actually an angle in the second quadrant. So what we always have to be aware of is, are we actually trying to find the inverse trig function, or are we simply using that inverse trig function to find what we're looking for? There's a big difference in saying, when is theta, or what is theta, if sine theta is equal to 2/5. And what is the inverse sine of 2/5? Now both of these things are after the same sort of thing. They're both looking for theta. But over here on the left, this is saying any theta will work. Doesn't matter if it's a single rotation, if it's in the first or second quadrant, it is positive, so it has to be in the first or second quadrant. Versus on the right, it's saying there's only one in particular that will work. So when I take the inverse sine in my calculator, let's see what we get. If we are using degrees, we would get an angle of 23.58 degrees. And in radians, that would be 0.4115. But that is just what the calculator is giving me for the inverse sine. But if the original question is really, what is theta if sine theta is equal to 2/5, I'm going to have to start off the same way. To solve this problem, I'm going to say, well, let's set up inverse sine of 2/5. But then I have to say, well, wait a minute, this is one answer. Another answer could be in the second quadrant. It could be 180 minus this, or 156.42. Or it could be any chi-terminal angle from there. And so I could add that 360n to it, or n is just any integer. And that would be the complete solution set. So we want to be really, really careful if we're choosing to use that inverse trig function, or if the problem has actually asked us for that inverse trig function. We need to be aware of the domain range for all of these trig functions. We need to be aware of their domain ranges for the inverses, how we restrict them, and that will help us solve any problem with these inverse trig functions.